Hello, everyone, and thank you for joining us for today's webinar, The State of Deep Learning, an Introduction to Deep Learning with RapidMiner. I'm Haley Matissa with RapidMiner, and I'll be your moderator for today's session. We're joined today by Philip Schlunder, data scientist here at RapidMiner. Philip has a master's in physics from the Technical University of Dortmund and focused on astroparticle physics and statistics during his studies. We'll get started in just a few minutes, but first, a few quick housekeeping items for those on the line. Today's webinar is being recorded, and you'll receive a link to the on-demand version via email within 1 to 2 business days. You're free to share that link with colleagues who are not able to attend today's live session. Second, if you have any trouble with audio or video today, your best bet is to try logging out and logging back in, which should resolve the issue in most cases. Finally, we'll have a question and answer session at the end of today's presentation. Please feel free to ask questions at any time via the questions panel on the right-hand side of your screen. We'll leave time at the end to get to everyone's questions. I'll now go ahead and pass it over to Philip.
Thanks, Haley. Hi, everyone. My name is Philip, as Haley just said, and today I'm going to talk with you about the basics of deep learning and how you can apply them inside RapidMiner with our new Keras extension. So what's in store for today? We're going to have a quick look at what you need before we get started. We'll talk about some things to consider before you apply deep learning. And then we'll have a brief look at what's deep learning. And I'll try to do that with as little math as possible. And then we'll have some demo time where I'll show you how you can apply it inside RapidMiner. So what do you need so you can get started? So hardware-wise, the minimum requirement is that you have a computer, PC or Mac, that is able to run RapidMiner. And we'd like you to have NVIDIA GPU in your machine to really take advantage of the TensorFlow capabilities that come when using Keras inside RapidMiner. The point of using NVIDIA is based on the whole deep learning community relying on some drivers that currently are only available for these type of GPUs. So the optimum, of course, would be to have a dedicated server with multiple GPUs. But that's just the ideal case. So that you know, Keras is a high-level deep learning framework, and it can rely on multiple backends. So for example, you can use TensorFlow, Microsoft's Cognitive Toolkit, or Theano, and you can choose what you want to use for your deep learning scenario. Software-wise, you need RapidMiner Studio or Server, depending on where you're going to apply it. Then you need a Python installation, a fairly new one with Python version 3.5 or higher. So, the Pandas Python library, and then we have some recommendations based on your operating system. So for Linux, it's most easy to use TensorFlow as a backend for Keras. And especially when you want to use GPUs, there's a special version of TensorFlow for GPUs you need to install. But we have great installation instructions for you. So when you're on Windows, it's more easy to use the Microsoft Cognitive Toolkit, but you also can use TensorFlow as well. You just need to make sure that you've installed it, and then you can download our Keras extension from the RapidMiner marketplace, set the path to your Python up, and you're good to go. But what do you do if you don't have a NVIDIA GPU? Well, we got you covered. Since RapidMiner 7.6, you have the ability to spawn a RapidMiner server within minutes inside the Amazon, AWS, or Microsoft Azure platform. So maybe you already have your data at one of these platforms, and you can just spawn RapidMiner server, install Python and TensorFlow, for example, and run the Keras deep learning extension. So one question is now, when should I try deep learning? So one good starting point might be you've tried multiple models and you're stuck with your current values and you've tried it all. And then you might think of, hey, I need a new method. So then you could try deep learning. So maybe it might help you increase your accuracy. Another situation might be that, well, you actually already have a huge amount of training data available and you want to see what the data can tell you. Or you have a very specific use case that you want to develop over time, because as we'll see over the next hour, it takes quite some tuning to get a good model when doing deep learning. Another scenario is that you need the notion of memory. So for example, when you are analyzing some text and you want to have a connection between something that's at the beginning of the text and something that's at the end, and in between there's a huge amount of words and sentences, and you need to somehow have the memory of what happened at the start, then it might be a good idea to try out some deep learning. Or when you're dealing with multidimensional input data, for example, when dealing with pictures or word vectors. But there are a few things you have to keep in mind. So since we are dealing with tens of thousands of parameters that need to be tuned, but don't worry, you need to do that yourself. With Keras, since it's a high-level library, you only need to set up a few parameters, and it does the fine-tuning of these tens of thousands of parameters for you. But still, you often need quite a huge amount of data. There are methods to avoid that, but you have to keep that in mind. And if you're in that situation that you need a lot of data, you need to ask yourself if your infrastructure is suited for that. And since it might take quite a while, and even maybe a dedicated server with multiple GPUs to be able to work on that huge amount of data, you need to ask yourself if the return of investment is really worth it. Because if you can only improve your accuracy over a few %, you might ask yourself if the return is really worth the investment. And since I just told you that it might be the case that it's very domain specific, since you need quite a lot of time to fine tune it, it's quite hard to use the model you trained for one scenario for another scenario as well. Yeah, and another point to keep in mind is that since the model that is built when doing deep learning is often very complicated, understanding any reasoning is impossible or very hard at all. There are possible techniques like using local interpretation methods, and we have an operator for that, which might help you. But you always have to keep that in mind, because there are new laws coming up, for example, in the EU, that want you to explain why you refuse, for example, a customer for a certain product. So after getting that away, let's talk about deep learning. So let's get started with a basic machine learning process. For those of you who haven't seen these thingies before, this is a snapshot from RapidMiner, and this is a process. And in it, you can see 4 operators. And an operator can do stuff with your data, or it can get you the data, or it can deliver the data somewhere else. So here you can see our first operator is loading the data. Then we're splitting it into 2 sections. And on one section, we are training a model. So there we know what we are interested in. So for example, the market value of a shopping basket in an online store. And we want to find a pattern in the other data that is available for this customer, for this purchase entry. And that's what is called training a model. And here we're doing it with a method called logistic regression, but it's not important which model we're using at this point in time. And after you obtain this model that somehow captivates the structure of your data or some hidden patterns, you can apply this model to unseen data. And in this case, since we are putting in data where we already know what's happening, we can check if our predictions made by the model were right or not. So this would be a very standard machine learning process, and you can have multiple operators in between and do fancy stuff. But now let's assume that we see the result, our prediction, as a regular input attribute. So before we had some attributes A, B, C, and now our target attribute is seen just as one of these input attributes. And we are going to reuse it again and do the same thing over again. So here we would say, okay, let's do the same thing again and create a new model, do another training, and check our new prediction. But now we already feed in the prediction of the previous model without knowing that it's a prediction. So what we can identify is that we have some input block, and then we have, well, a first model, which can be seen as a first representation of the pattern in the data. And then if we do it again, we have a second representation. The first one might be very rough, and the second one might be more detailed and more focused on other things. So if we see these blocks now a bit separated from our process, this is, by the way, called hierarchical learning. So we are building a structure of representations from one thing we've learned onto another. So we could do this over and over again. And by the way, hierarchical learning is often called deep learning as well. It has nothing to do at this position that I used more representations, but you can think of that I could easily insert like 3 more blocks of these operators and do the same thing over and over again. So now let's focus on these blocks we've just seen. And as you've just seen, I call this deep learning, but many of you might have thought about deep learning with regards to neural networks. And that's not wrong, because many people are always using deep learning as a synonym for deep neural networks. But don't worry, we'll focus on deep neural networks now, but I just wanted to highlight you how you can go from regular machine learning to deep learning, and even without using neural networks. So now I just used these blocks where one was the input and one was the first representation from our first model building process. And then we had another model building process, and here we have 3, the 3 blue ones. And let's call these layers. So we have an input layer and then an output layer. And in between, the ones are called hidden layers. And since we are now slowly going in the direction of a neural network, we're going to talk about neurons. So when you feed in your data, you can think of that you might have 3 input neurons because you are having 3 attributes. And then at the output, it depends on if you are doing machine learning for a classification case or for a regression. In terms of classification, you might want to know if someone is going to churn or not. So you have 2 possible answers. Then you would have 2 neurons at the output layer. And if you would do a regression for one value for the market, the basket value, for example, you would have 1 neuron. So in between, we could have as many neurons as we like. And as you might have guessed already, these are somehow connected, and we'll talk about this connection a bit more later on. But let's first identify what these neurons in the hidden layers are about. So as you can see, I've highlighted the 3 neurons, so the 3 attributes in the input layer. And the neurons in the first hidden layer are somehow a mixture of the previous attributes. So it might be that the first attribute of the input data takes up a majority of this mixture, and the others only play a minor role. But then again, it's not only this mixture, but there's also some function you apply to it to check to what extent this mixed up value amounts for the neuron. But what you can see here is I've called the first blue block a few slides ago the first representation. And what you can see here is that I'm building a new representation by creating new attributes through meshing up the previous attributes. So for the next hidden layer, I would have mesh up of the attributes beforehand that are somehow a representation of the initial attributes. So we can have more and more abstraction the deeper we go in a neural network. And you'll see that, like in this slide, I talked about this activation function, and one of the activation functions you can use inside the Keras extension is called rectified linear unit, short ReLU. And if there's a text on the slides that has some grayish background, this means this is a word or an option that might pop up in the Keras extension. So you've already seen it and you might recognize it when playing around with it. So these layers that are completely connected with the previous layers are called fully connected or dense layers. So what we're going to do now is talk about a few different types of layers that you might encounter during your creation of a deep learning architecture. And well, here you can see it's really important to see that each neuron of one layer is connected with all neurons of the previous layer. It might be that I've missed a connection. I hope I didn't, but this should be the case. So now let's go to another type of layer. And for that, let's change perspectives a bit. Here you can see that I slightly changed the type of input data. Now it looks a bit different because, well, now we're going like 4 steps in the depth. But just follow me a bit and see where we end up. And what we're going to do here is go to a new type of layer, which is called a convolutional layer. So you should see that 4 neurons in the first hidden layer are in some kind of dark bluish region. And these 4 are connected with 1 neuron of the second hidden layer. So here, only part of the neurons of the previous layer are connected with the neuron of the next layer. Again, for the fully connected layer before, a neuron of one layer was always connected to all neurons of the previous layers. So if we lie this down flat on the table, it looks a bit different. And here you can see the first hidden layer and this bluish box surrounding 4 neurons. And what we're going to do now is learn that this box is called a filter. So in a convolutional layer, you apply a filter which has a given size to part of the layer you're looking at. And if you do that, you end up with something called an activation map. And so here you'll just see that, for example, if our hidden layer, which is a convolutional layer here, has a size of 4 by 4, and our example filter has a size of 2 by 2, we end up with a 3 by 3 activation map. But this is only because we're using something called a stride. And this is not complex. This is just the step size we are using when moving from one region to another. So as it's called a filter, we are always looking at one part of this layer, and we can move this region which we are currently observing. So since we moved this region by 1 neuron to the right, the stride, the step size, is equal to 1. Okay, so then you could do some calculations and find that out also, just in case you're curious. So now let's fill up our layer with some values. And just so you know what's happening under the hood, here, if we would have a filter that is filled with 1001, and we would apply this to the first region, we would always multiply 1 value with the one lying underneath. So here we'd have 4 times 1 plus 3 times 0 plus 1 times 0 plus 7 times 1. And what you see, since we have some diagonal structure in the filter, we are just adding up the diagonal values. So here we're adding up 4 and 7, and this gives us an 11, and is the first value of the activation map. And then we move one step to the side because the stride we set up was 1. So now we are focusing on this area, and here again, we're just adding up the diagonal values. So 3 plus 8, and we end up with 11. And we're going to do that with the next section. And don't worry, I'm not going to do that for everyone. But I just wanted to show you that the next step would be from the right side to just go one down or go diagonal one down. And then it's always one step. So one step to the right or one step to the bottom. And then if we are finished, we have one activation map for this example filter. Just a short note, because it's an important setting that is often used for convolutional layers. There's something called padding, and this is filling up the area around your layer with 0 values. This allows you to have the filter focus more on the border values as well. So here you can see I've chosen a padding with size 1, and this means I've added zeros. I've added one row and one column to each side with zeros. Okay, so if we go back to our 3D-ish perspective of our convolutional layer, we've just learned that not all neurons are connected with all previous neurons. And there's a region which is called a filter, which we move over this layer to get something called an activation map. And for each filter we apply, we get different activation maps. So you can specify how many filters you want to have, and then you could have, I don't know, 96 filters, and this would leave you with 96 activation maps. And this collection of one layer, which is used for scanning, and then these activation maps you get from moving this filter above this layer, this single thing is called one convolutional layer. The next type of layer that is quite important because it's often used in connection with the convolutional layer is a pooling layer. So for a pooling layer, again, we have a filter of a given size. Here it's 2 by 2 again. And then we have different types of pooling which we can apply. And here we're applying something called max pooling, which is short for maximum pooling. And as some of you might have already guessed, you observe this window, this 2 by 2 window, and find out what the max value is. And here it's 7, so we put in 7 in our new resulting layer. And then if I would use a stride of 2 just to highlight the difference between a stride of 1 and 2, here we would have 8 as the highest value. So we would put in an 8 in our next layer. And then since the stride is 2, we are going 2 neurons downwards. And here 9 is the highest value. And for the last section, 4 is the highest value. And this is, as you might think, one option besides many. And another one is to use average pooling. And here you just add up all the values of the region you're looking at and dividing it by the number of entries. So for the first section, you would end up with 15 divided by 4. And then you can do that for all the sections. So this pooling is used to reduce the size of your layer. Here you can see before we had a layer that had a size of 4 by 4. And now we have a layer that is of size 2 by 2. This might help when you have if you have very big layers, then you have many values that you need to optimize. We learn about that in a few minutes. And you don't want to have that many values to optimize, because the less values you have to optimize, the less data you need. And if you had a convolutional layer before this pooling layer, this pooling is applied to each one of the activation maps. So if we had a convolutional layer with 32 filters, so 32 activation maps, we now have 32 activation maps in the pooling as well. So let's get to the next layer. This one is a bit tricky. This one is called a recurrent layer. And as you can see, I've added some labeling to this layer. And here it says S0, and this is to indicate that these layers have a state. So recurrent layers are used if you have sequential data. So for example, if you have a sentence that consists of multiple words and you are analyzing these words, and then pouring in one sentence as one data point, you would have multiple words per sentence. So you would need to deal with that. So one word would be one state that is changed. And the trick here is that the output of one layer is fed back into, can be fed back into the same layer again while changing the state. So let's look at this a bit differently. So this is the same concept. I just wanted to try to highlight it from two sides. So this might help a bit, I guess. So here we have one data point. It's one phrase, I drank some coffee. And now I'm feeding it in the network. And first the I is fed in, and the state of my first hidden layer is S0. And then if drank is fed in, we are at the next state, and all the time values are changing inside this hidden layer. And then some, and then coffee. And then we're going to the next layer. So this is nice, but in many cases, this idea of a recurrent layer is only used as a base model, and there are multiple methods based on this idea that are more helpful, because here we have, for example, the idea that we want to find out what someone drank based on the sentence. And well, I said drank, and then coffee is just separated from the word drank with one word in between. So drank, which is in state 1, and coffee, which is in state 3, has only state 2 in between. But since you're doing some calculations from one state to another, you could say that the focus is lost. It's a bit abstract to say it like that, but yeah, I guess if we look at a longer text, for example, we would have a text starting with drinking a hot beverage, that, and then follow some longer explanations, because I like to talk in long phrases and sentences, and then it ends later on with, for me, it is coffee. Well, at the beginning of my rambling, I had the word drinking, and I now want to relate it to the word coffee. But if I have, I don't know, some 90 states in between, my network lost focus of what's important. And that's why there's a concept of long short-term memory. And this is, it looks complicated first, but if you're viewing it a bit abstract, as we are doing right now, it might be not that tricky. So for each neuron, you can see now that we zoomed into a neuron, you have multiple values that are used. And so we always have a previous state, except when we are at the first state of a neuron. And then we have some functionality. we have 4 values that help us say, for example, that we don't want to store the information we get at all, or that we only want to store part of the information inside this neuron. And this is always considering the previous state. So you can imagine that if I'm at this long text with drinking at the beginning, the network will see that, well, the next word has no relation to what I'm looking at when I'm looking back at what I've just heard. So if you go back a moment, we had drinking a hot beverage, that. So if I'm at that, then I've heard drinking and a and hot and beverage. But I've seen that over time, looking back at the previous things I've learned, that there's no meaningful information about what I drank. So you can say, okay, the current word is not important to me. I only store part of the information, so I can, only store part of it. I can completely forget about it because, well, it turned out the information is useless. Or I could use the information, but only a minor part of it when going to the next state, to the next word in this example. And then this helps the network to somehow keep focus on what's important. Okay, so then we have a last type of layer I want to talk about, and this is called a dropout layer. And dropout is a method that is used for regularization. So what does it do? Well, it helps you reduce the complexity of a model because if you're creating a very complicated model, it might be that you're just learning the nuances of your training data. And you don't want to do that because then if slightly different data comes in, you won't recognize it because you just learned by heart what's inside the training data. And for a neural network, you can do that by randomly dropping out some neurons. And for that, there's something called the dropout rate, and it's a probability. So it's between 0 and 1, so 0% chance of dropping this neuron, or 100% chance. So we would drop all the neurons and it's pointless to create a model at all. Okay, so before we can apply this, we need to ask ourselves what to do with the data. There's some minor setting up you need to do when feeding your data inside into the Keras extension to create a deep learning architecture. And we need to learn how to create this type of architecture now that we've learned a bit about the basic concepts of these layers. So looking back at our neural net, we're just going to focus on the input layer. And what you need to set up is something called the input shape. So in RapidMiner, you'll later see that we have a Keras model operator, and you can open it up, and inside you'll put all the nice layers we've just learned about. And in order to do that, you first need to tell it, well, what's the data like? And here again, we have our 3 attributes, our 3 neurons in the input layer. And well, there's one tricky thing you need to know when building the model, what's your first layer. And if it's a convolutional or recurrent layer, it needs to know how many steps or time steps are in there. Because if you think back when we just talked about the recurrent layer, we had multiple words. So it needs to know how many words are in a sentence. Or think about looking at stock exchange, and you want to make a forecast, and you have a window of a time frame of 30 time steps, and you want to use these for each forecast. So then this is the number of time steps you would provide. Right now here we only have 1 time step because we have 1 column in this way of displaying things. And we have 3 attributes. So our input dim, our input dimensionality is 3. But if we don't use any convolutional or recurrent layer, and we're just using a fully connected layer, for example, the input shape is just defined by the input dimension. So then it would be just a 3, as you can see on the right. But now, if we would have a data set with a time window of 4, you can see now that we have 4 columns, and for each of those we have 3 attributes. Then the input shape would be 4, 3. And there's one more thing you need to learn about the input data. Well, looking at this whole box, this orangey box, this is our complete data set right now. And each column represents one entry, so one data point. This could be a picture, a sentence, or whatever. Or it could be a series of time events. And then it might be the case that we have quite a lot of data, but we want to reduce the training time, or we don't have that much data, and then still it might help to group up the data in batches, and this is just a collection of entries. So the notion of a batch is just a selection of, here, for example, 4 entries. So you can define a batch size, and then for each optimization step, we learn that in a minute, only 4 entries are sampled, so picked from your data set to obtain this value that you need to create your model. Okay, so going forward, we need to understand what a weight is. So we've seen these connections before, and they are called weights. This is because they define the portion of a previous neuron's information that we're going to need, are we going to use for the next neuron. So here, a thicker arrow indicates that a bigger portion of the information of a previous neuron, so a previous attribute, is used for the next one. And these weights are the things that the model needs to learn during the training process. So yeah, we have weights between each layer, and altogether are the weights. And then, as I've just said, there's a method that optimizes these weights, so it gradually changes the weights and then looks at the output of our network to check how good the result is. Because we're doing it in a supervised way, this means that we know what's correct because we have historical data where we already know what's the price of the basket value, for example. So we can take the result we're getting from our model and compare it to the real value, and then we see how good we are. Now this is measured in something called a loss, and this loss is different for different types of application. And if you feed in one batch of data, so this could only be like 4 entries, many times it's like 32 entries or even more, or the whole data set, and you feed it through the network one time, this is called an epoch. And if you're doing it multiple times, so maybe 100 times, then you would have 100 epochs, and all the values of the previous epoch are used as a starting value that are then slightly changed during the next epoch and then checked again for the loss. And this method is called optimization. Okay, and now let's look on the different types of use cases. So if we have a binary classification, or this means we just want to know if somebody, for example, is going to churn, yes or no, or we could have a multi-class classification where we want to know the color of something, is it red, green, or blue? So multiple values are possible. Or we would have a regression where we want to estimate a certain value, for example, the price. Then it's often a good idea to use ADAM or RMS prop as an optimizer. These are options inside the Keras extension. And then you always need to change the loss that is used to check how good you are. And so we have binary cross entropy for binary classification, categorical cross entropy for multi-class classification, and mean squared error, so MSE, for example, for regression. And RMS prop is often used for recurrent layers in the network, and Atom is very similar but has some extra feature. And for that, then you can observe how the loss changes over time, so over the epochs. And it should decrease. And you can do that by looking at the history that is delivered through the history port of the operator, or you could use a tensor board, which offers you a view in your browser to check on the values while they come in. And if you see a bump in there, you need to change the initial weights, because for the first epoch, you need some starting values for the weights. And then if it lowers too slow, something called the learning rate is too low. This is the amount of change you introduce with regards to the previous weight value. So you have a weight value and you want to change it. And if you're only changing it slightly, then you have a low learning rate and so on and so forth. And I just leave that in here. So if you get the slides, you see how you can set up the tensor board to look at the values. So when setting up a model architecture, you would always start with the input. Then often you have a convolutional layer and maybe another convolutional layer, and then a pooling layer to reduce dimensionality. And often the size of the filters changes over time and the number of filters as well. And then if you find out that, well, the combination of a convolutional, and a pooling layer is great, you often repeat it and have multiple blocks of the same in your network. And then you could use, for example, a recurrent layer at the end or a fully connected one, and then you obtain your output. So it's always good to start small, and then you want to test for overtraining or overfitting by using a very small batch size and see if you're getting a small loss and high accuracy, and then there are ways of doing something to prevent that. And well, then you need to change the so-called hyperparameters. These are the ones we just talked about, like the number of filters, the size of the filters. And here you can see that most of the time, the number of filters increases because you're going from a very rough view to more detailed look at the things, because each layer introduces a new representation. And this is reflected in all the other settings as well. For example, oftentimes you start with no padding, so no zeros around the corners. But later on in the network, you might introduce a padding because you want to focus on the border values as well, because you want to take in more detail as you go. So a brief summary about what we've just learned. There are different types of layers: fully connected, convolutional layers, recurrent layers where you can go back, and in convolutional layers, you're only observing one part of the previous layer, pooling to reduce the size, dropout to make sure that the complexity of your model is not too big. And then we learned that a model is defined by the setup of the layers and their configuration, and by the weights that obtained through optimization of the comparison of a loss value over several epochs, and that we need to differentiate between classification and regression. So for classification, we have the number of neurons at the end that relates to the number of possible values for our attribute of interest. And we would, for example, only have one if we would do a regression of one price. Okay, so how are we going to use it in RapidMiner? Well, we have multiple options. By default, we have a neural net operator. This is great when you want to get started and just want to play around with the basic fully connected layers. You have some simple options to optimize all the parameters. And then if you want to go deeper, you can use our deep learning operator from H2O, and it offers you more options for the optimization and multi-threading, so you can use all the threads on your machine. And then if you want to play around with advanced layers and you need GPU support to really take advantage of the hardware you have and throttle down all the data through your network, then you might want to try out the Keras deep learning extension. But as you might have guessed already, since we have multiple types of layers and things we can set up for them, it's a bit more complex. So let's start our demo. I'll switch over to RapidMiner, and after installing the Keras extension, you'll see that in your repository view, you have a folder called Keras samples. And in it, we have, for example, the iris classification sample, and I'm briefly going through it to tell you how you would set things up like that. In the iris data set, we have 4 attributes, and that's why with the Keras model operator, which you find when looking through the operator panel after installing the Keras extension, you here have the Keras model operator. And as you can see, we have multiple options in our parameter panel on the right, and there we need to define the input shape. Since for this example, we're just going to use no time steps and just no convolutional or recurrent layers, our input shape is just the number of attributes available. So here it is 4. And then underneath, since in the iris classification problem, you have 3 types of flowers you want to differentiate from each other, you are setting up the categorical cross entropy because it's a multi-class problem. And then we're choosing Adam as an optimizer here and use a random learning rate. It's often a very low value. And then it's important to set up the number of epochs. So this one would put in the data 128 times and always in chunks of 32 entries. And then we can open up this Keras model operator by double-clicking on it. And then you can see on the operator panel on the lower left that we have multiple types of layers. And here I took the core layer and another core layer. And when clicking on a core layer, you can choose between multiple types of layers. And if you're choosing the dense layer type, this is the fully connected layer, so the basic one. And here we're just going to use 8 units, so 8 neurons, and we're using this rectified linear unit as an activation function. And you can set up the initial weight value, which is called kernel initializer. And then as the final layer, the output layer, we're choosing a fully connected layer again. And here we're going to use 3 units because we have 3 class values, 3 types of flowers, and a softmax activation function. Okay, so then we can run it, get the model, and can apply it to our data set here. Before I do, instead of doing that now, we're going to switch to another example because I want to show you the results inside the TensorBot as well. And here we have some stock price information, and we are only going to look at the closing dates of these stock indices, normalize the data, so center them around the mean value and around 0, and then use the windowing operator to always select just 30 time steps and see them as one data point, because we want to use 29 values to predict the 30th. And then we feed in this data into our Keras model. And here, since we're going to use a convolutional layer inside, we need to provide the number of time steps as the first value, so 30, and then the attribute that has information in it. And for this case, it's only the closing date because we're only looking at that. So we'll only have 1 as the second value. And inside, you can now see that you can easily just put together the different types of layers as we've just seen in the presentation. So very abstract and very easy to do. And then on each layer, you can say, okay, this is a convolutional layer, and it's one-dimensional because it has the thickness I've just shown you in the presentation. and it uses 64 filters, and all these filters have a size of 2 by 2, and our step size is 1. And we're not going to use any padding here. This is the valid option. And then afterwards comes a pooling layer and another convolutional layer. And we're going down and we tested that. And then we have some more layers here. So one dropout layer, as you can see, it's part of the core layer as well. And you can select the dropout option to reduce complexity of the model. And important here is that at the output layer, we only have one neuron in it because we have one value. So the 30th time step we want to predict. And if you run this, you can set up something called a callback, and then you'll end up with values that are stored in a folder, and you can view it in your browser to see how the loss goes down. So let me enlarge this. Here you've seen there are some messed up values in it from previous tests as well. But what you see is on the y-axis is the loss, and it should go down. And on the x-axis, you see the number of epochs, so the number of times I fed data into my model. So that's it from my side, and I'll hand over to Haley. So feel free to ask questions, and I'll see what I can answer.
Great, thanks, Philip. As a reminder to those in the audience, we will be sending a recording of today's presentation within the next few business days via email. So like Philip said, now it's time to get the audience questions. And you can go ahead and input those in the questions panel on the right-hand side of your screen. So I'll go ahead and take a look at those questions now. So the first question for you, Philip, is you showed other options besides Keras. Why should we use them?
Okay, I guess this relates to a previous slide where I showed this comparison. And as you can see, the Keras deep learning extension covers all the things the other extensions have as well. But you have to keep in mind here that due to the additional number of options you have when choosing how to build your network, like new types of layers, the convolutional layer and so on, you have so many options that it can feel overwhelming at the beginning. So it's always a good idea to start with just a basic neural network and then play around with that. And then if you feel comfortable, you can try to use the deep learning from H2O. And maybe your data set isn't that big as you thought, and it's already good, can already be handled great by your machine with multiple threads. And then if you still feel stuck and you have some GPUs and you want to try out new layers, then you can set up Keras with TensorFlow using Python, and then you install our extension and you can easily set up the layers as I've just shown without having to fine tune all the things you had to fine tune before. Great,
thanks. The next question here, I believe this was asked earlier in the presentation. This person was asking, why do we need to split the training data 2 times if we already did it once?
Okay, so I guess this is referring to me using the split data operator. And here, this was just a minor step of the data mining process. So the first part of the training data, we are always using one part of the training data to create a model and then check the predictions against the data we didn't look at. And after doing that, we get a first feeling on how good our model is. And in general, you would have to do this multiple times in terms of a cross-validation to see how good you perform on average. And then you would always have to have another data set in the backhand, so another split before that with data that you haven't used to optimize the parameters of your network. And then you can check against this evaluation data set to really check on completely unseen data, which you haven't used for optimization, how good your model performs in general.
Thanks for that. Another question here is, this person says, I installed the Keras extension. Do I need to install TensorFlow and other things as well?
Yes. In general, you would start by installing Python on your machine if it's not already there. Then, depending on how you install Python, if you just install it through the Python website, or you are using a Linux, you often have Python pre-installed, then you can use pip, which is the package manager for Python, to install TensorFlow by using pip install TensorFlow. Or if you used Anaconda, it would be conda install TensorFlow. And if you want to use your GPU, and it's one from NVIDIA, you need to check that it's TensorFlow minus GPU, I guess. But you can always use the search function of pip or conda to search for the specific library. And after doing that, and you install Keras again inside Python, and then you can start RapidMiner, load the Keras extension, and then provide the path to the Python on your machine to use it inside RapidMiner.
Thanks for that. Another question here. It seems that the selection, ordering, and combination of types of layers is critical to generate a good model. What references or guidelines do you have that can help us make wise choices about these layers?
Okay, this is a very good question. Well, it turns out that there's a lot of experience in that, and thinking about the problem. For example, if you're looking at image data, you often want to have first very abstract layers. So you would have bigger filters and fewer filters maybe. And a general great course is the one I'm providing in the slides as sources. It's a Stanford course 231. It's a bit more mathematical than what I've just shown, but it's in general a very, very good guide on learning how to set up the architectures. And often it's a very good idea to go, for example, to this lecture or other places and learn about previous networks. So in the history of deep learning, the networks got deeper and deeper, and then there was always a shift of concepts. And there's, for example, a network called AlexNet. So general structures of networks have names because, well, they are so well known. And then try to look at networks like AlexNet or ResNet and try to understand what they did. And then I guess you would get a great feeling on how to set up the layers.
Great, thank you. Another question here, this person is asking, where do I find documentation for the Keras extension?
Okay, right now there's some documentation inside the product. So if you have the extension opened up, you have the help view inside RapidMiner. And then we have our great community where there's already a thread for the Keras extension. So if you're curious now and you want to play along with our Keras extension, please go ahead. And I'm very certain that you might run into some questions. Then go ahead into our community site. You will find it on rapidminer.com as well. And there you can ask questions. And in general, it's always a good idea to look at the Keras docu itself. It's linked in the slides as well. It's keras.io.
Thanks, Philip. Another question here. This person is asking, how would you represent a word or entire sentence? That's their first question. And then the second question is deep learning suitable for natural language processing?
So I'd like to answer the second question first. Yes, it is, especially due to the recurrent layer type and the concept of long short-term memory. It's heavily used in natural language processing because you have this potential of keeping the focus over a long distance of words. And to the first one, you can represent it by using a tokenization. So you would often you divide a sentence by spaces or any other characters to just get the single words. Then most of the time you remove so-called stop words, so filling words, which I hopefully didn't use that much during this presentation. but they also can be words like the and a, and then you have a vector of these words, and you can create, for example, word2vec as well. This is using a network to create numerical representation. We have one extension coming up, which is called word2vec, and you could use that to create a representation as well. But we already have a text mining extension where you can use frequencies of words to get a numerical representation of sentences as well.
Okay, thanks, Philip. So for those in the audience, it looks like we're just about time here. If we weren't able to address your question here on the line, we'll make sure to follow up with you via email within the next few business days. So thanks again, Philip, and thank you everyone for joining us for today's presentation, and I hope you have a great day.
Thanks for having me, and thanks for attending, everyone.